Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up section 11.8 from your textbook, which was our introduction into power series. Remember that a power series is a function that when you input a x value gives you an infinite series. And these power series, we consider them well defined if the series that they output is a convergent series. And we defined a concept similar to the domain, which is the interval of convergence. And remember, the interval of convergence is the collection of all x values that when inputted into your power series return a convergent series. So in our last video, we took a look at a couple of examples, 3 examples in particular, where we went through and we determined computationally the interval of convergence. And then we made a comment that those 3 sort of examples actually summarize the 3 possibilities for the interval of convergence. So the first thing we're going to do in this video is take a look at a theorem that confirms that the 3 possibilities we saw in the previous video are indeed the only 3 possibilities when it comes to interval of convergence. So let's go ahead and talk about this theorem here. This theorem says we have a power series, sum a sub n, x minus c to the n. Remember, this x equals c is the center of our power series. Then this theorem says that there are only 3 possibilities for the interval of convergence. First, the power series can converge everywhere, meaning that any x value you plug in returns a convergent infinite series. That means that the interval of convergence is negative infinity to infinity. The second possibility is that the power series converges only at its center. Remember, we discussed in the previous video that a power series is always going to converge at its center, because if you plug in x equals c into here, you're going to get it's going to zero out all the terms there, so you're going to definitely get something that converges. So it is possible that the only spot that the power series converges at is at the center. If that's the case, then the interval of convergence is just the single value x equals c. The third option is that the power series converges on a finite interval, and that finite interval is centered at the center. That means that the interval of convergence can be written as the center minus some number r, all the way up to the center plus some number r. And we choose to use the letter r here for a very sort of specific reason. In the last situation, we call that r the radius of convergence. And it really makes sense to call it a radius, because if you imagine this interval sort of visually, what you have is you have your center here, and then you have your center plus r here, and you have your center minus r here. And the distance between the center and those 2 endpoints is r. So it really makes sense to sort of think about it visually as a radius. All right, some other notes. Case 1 and case 2, they don't technically have an interval. I mean, I guess this one has an interval of everything, but they don't have a finite interval like here. But we can still apply this concept of radius of convergence in these situations. In case 1, we often say that the radius of convergence is infinity, because the interval of convergence is everything, so the radius, or the sort of width of the interval, is infinity. And in case 2, we often say that the radius of convergence is 0, because you are basically saying that you can't go anywhere beyond the center to have convergence. So we can actually talk about the radius of convergence in all 3 situations. Here it's infinity, here it's 0, and here it's some finite positive value r. And then also remember, in case 3, we saw an example of case 3 in the previous video. You need to analyze the behavior of the endpoints individually. You might end up where both endpoints actually diverge, so you have open parentheses on those intervals. It could be that both endpoints converge, so you have hard brackets, they're included in the interval of convergence. Or it could be something where one converges and one diverges and one converges, or where one converges and the other diverges. So all the possibilities are really possible there. But what's so important about this theorem, the really big idea here, is that these are the only 3 types of interval of convergence you can have. It can either be everything, only the center, or an interval that is centered at the center. That means you're never going to have an interval of convergence that's like the center and then everything bigger than the center. Or you're never going to have an interval of convergence that is some stuff in the center and then some more stuff over here and maybe some stuff over there. It's always either got to be everything, just the center value, or some interval that goes on equal distance on both sides of the center. That's really the power of this theorem. All right, now that we've sort of talked about what these three possibilities are, it's time to go ahead and take a look at some more examples to make sure that we're comfortable computationally determining the radius and interval of convergence, and also to sort of really cement to you guys that really these are the only three possibilities. So in each of these examples, we're always going to run into one of these three situations. So let's go ahead and take a look at those examples. So for our first one, we are going to determine the radius of convergence and the interval of convergence for this power series. So we have the power series n equals 1 to infinity, 1 over 6 to the n squared times x minus 5 to the n. So the first thing we'd like to always do is identify the center. The center here, of course, is at x equals 5. So we know that either the interval of convergence is just going to be x equals 5, everything, or some interval centered at x equals 5. So let's figure out which one it is. Now, if we look at this, we'll notice that everything is just multiplied and divided. So we could go ahead and use root test because it'll be easy to distribute in a power of 1 over n to everything. If you want, you could also certainly use ratio test, but root test, if you're comfortable with it, is oftentimes a little faster. So let's try root test here. So for root test, we're going to be looking at the limit as n goes to infinity. We'll put these terms in absolute value, 1 over 6 to the n squared, x minus 5 to the n, absolute value 1 in the absolute value, and then to the 1 over n exponent. All right, now what we would like to do is we'd like to distribute this 1 over n exponent onto all the pieces, but to do that we might want to first begin by recognizing that these absolute value bars really only apply to that x component. So let's rewrite this as the limit as n goes to infinity, 1 over 6 to the n squared. That, of course, is always going to be positive, so no need for absolute value bars. Then absolute value x minus 5 to the n. Again, this is what's going to be an absolute value because we don't know what x is. So subtracting it by 5 might result in a negative number. We don't know. And then all of that to the 1 over n exponent. Okay, now we can apply this 1 over n exponent onto each term. So it'll go here, here, and here. And of course, power to a power, we're going to multiply out those exponents. So we get the limit as n goes to infinity. Looks like we're going to get 1 over 6, n to the 2 over n, and then absolute value x minus 5. And that's because power to a power we multiply, they're going to cancel. 2 times 1 over n is going to be 2 over n, and then n times 1 over n also going to cancel. All right, now the sort of trick is to recognize that this no longer has an n involved in it, so we can bring this outside of that limit. So we get that the absolute value x minus 5 times the limit n goes to infinity, 1 over 6n to the 2 over n. Could we bring the 1 over 6 out? Sure, definitely. I like to just move the absolute value and then focus on this limit, but it doesn't matter. You could certainly bring out the 1 over 6. Remember that this n to the 2 over n, whenever we're working with root test, we often need to make use of the limit as n goes to infinity of n to the 1 over n is 1. So we'd like to rewrite that. So we can say that this is absolute value x minus 5, limit n goes to infinity, 1 over 6 times n to the 1 over n, and then squared. Because obviously 1 over n times 2 gives us that 2 over n. Power to a power, we always multiply. Now we're comfortable in saying that that is x minus 5 times 1 over 6 times 1 squared. And it looks like we get absolute value x minus 5 times 1 over 6. Okay, so that was performing the limit computation necessary for the root test. Now, remember, we're interested in convergence. So to converge, we need this limit, absolute value x minus 5 times 1, 6, to be less than 1. Okay, let's go ahead and isolate this absolute value. Let's multiply this over onto the other side. So we get absolute value x minus 5 is less than 6. Now, we could go ahead and solve this. Remember, you could change this into x minus 6 less than x minus 5 less than 6, like a double inequality, but there's no need to. This actually is the perfect format for us. This is telling us that x can be no more than 6 units from 5. So this right here tells us the radius of convergence. Once we've isolated our absolute value, what is over here is telling us our radius. So we now know that the radius of convergence is 6. What does this tell us about the interval of convergence? Well, we know that it's centered at 5, and it has a radius of convergence of 6. So 6 units below 5 would be -1, and 6 units above 5 would be 11. So the interval of convergence is from -1 to 11. If you want, you can check on your own and actually use the double inequality, -6 less than x minus 5 less than 6. Add 5 to everything, and you'll get the same thing here. Okay, you'll notice, though, that my interval of convergence, I haven't written in hard brackets or soft brackets because we need to test those endpoints. But at least now we know the radius of convergence, and we know the interval of convergence, except for the behavior at the endpoints. So let's go ahead and give ourselves another page, and let's test those endpoints. So we got to test the endpoints here. So it doesn't matter which endpoint we start with, but let's go ahead and start with the lower one, x equals -1. So we'll have the sum from n equals 1 to infinity, 1 over 6 to the n, n squared, plug in the -1, minus 6 to the n. Now, when you're doing this, a trick you're going to see over and over again is that whenever you plug in the x, any of the exponential terms should be gone. Because when we plug in x, this is always going to give us an exponential, and the whole point of root or ratio test is to figure out how big that x can be. Those endpoints are going to be exactly at where the exponential cancels out. So you'll notice that this cancels with this. We'll be left with that -1 to the n. So I guess we're going to get something that looks like -1 to the n, 1 over n squared. Now, what do we know about this? Well, if we were to put it into absolute value, it would converge. Or if we just use AST on this directly, it would also converge. Notice that when we're talking about endpoints, we don't care if it converges absolutely or conditionally. We're just interested in whether or not it converges, because we're interested in what we call the interval of convergence, not the interval of absolute convergence or the interval of conditional convergence. So we're just looking for convergence here. So this converges. If you want, you could say by AST, since that's pretty clear. That limit goes to 0, and it's strictly decreasing. So we know that at x equals -1, our power series converges. Now let's also try the other endpoint, which is x equals 11. Here, if we do that, 1 over 6 to the n, n squared, plug in the 11, which would give us 6 to the n. Go ahead and we would cancel these, and then we'd get the sum from n equals 1 to infinity, 1 over n squared. So 1 over n squared, this converges as a p series this time, because this is just 1 over n squared. So both endpoints converge. So what does that tell us for our interval of convergence? Well, our interval of convergence was from -1 to 11, but we just figured out that it does converge at each endpoint. So we can put hard brackets on both of those. So our interval of convergence here is -1 to 11, including both -1 and 11 there. So there we go. There's another example of going through, determining the radius of convergence, which we found along the way to be 6, right, which is the distance from the center to the endpoints. And then we also determined the actual interval of convergence by figuring out what the endpoints should be and then testing those endpoints individually. Okay, let's go ahead and take a look at another one. So we want to determine the radius of convergence and interval of convergence of this power series, n equals 1 to infinity, n to the 5th over n factorial, x plus 1 to the n. First thing we want to do is mention the center, x equals -1, because we know that that's going to be important. Then we can notice that factorial, so we should probably try to go ahead and use ratio test. So let's go ahead and do that. Limit n goes to infinity. We got to plug in n plus 1, so I guess we get n plus 1 to the 5th over n plus 1 factorial, and then x plus 1 to the n plus 1. And then we need our a sub n term, so n to the 5th, n factorial, x plus 1 to the n. Okay, let's go ahead from there, and we'll do our standard sort of manipulation. We're going to bring this guy up, bring this guy down, and then we'll start looking for simplifications. So we have the limit as n goes to infinity. Looks like we have n plus 1 to the fifth. We have an n factorial and an x plus 1 to the n plus 1. That's everything that ends up in the top. And in the denominator, again, just trying to line things up, we have an n to the fifth. We have an n plus 1 factorial, and we have an x plus 1 to the n. All right, let's simplify as much stuff as we can. We're pretty comfortable canceling the n factorial with the n plus 1 factorial and getting just n plus 1. And here we can cancel this with this and just get an x plus 1 up top. So we should have the limit, n goes to infinity, absolute value, n plus 1 to the fifth, and then we get x plus 1. And down in the denominator, we have n to the fifth, and then an n plus 1. Okay, now we can do a couple things. Since we've sort of separated this out, all of this is always positive, so we know that that absolute value bar really applies to that. So let's just focus on that for a moment. So we have the limit as n goes to infinity, n plus 1 to the fifth over n to the fifth n plus 1, and then absolute value x plus 1. Now, of course, we can move this absolute value x plus 1 in front. So absolute value x plus 1, limit n goes to infinity, n plus 1 to the fifth over n to the fifth n plus 1. Now we can focus on actually doing this limit. It's very tempting, and it's not incorrect, but it will make things a little bit messier. It's tempting to cancel this with this and make that to the fourth. But then you're going to have to try to figure out how to deal with that n plus 1 to the fourth over n to the fifth. You could maybe make an argument that the numerator has a lower degree than the denominator, so the limit goes to 0, but that gets a little messy just to write out. There's actually a more clever way. Instead, remember that these two sort of are similar. They're from the ratio test, but we just didn't cancel them. They are both to the fifth power, though, so we can write them as a single expression. So sort of a more elegant way of writing this out is to view this as x plus 1 in absolute value, limit n plus 1 over n to the fifth over n plus 1. Why do we like this? Well, we know that n plus 1 over n, this is going to go to 1. So the numerator is going to go to 1 to the fifth, which of course is just 1. And down here, this is going to go to infinity. So this is going to tend towards x plus 1 times 1 to the fifth over infinity. And where is 1 to the fifth over infinity going to tend towards? Well, this is going to tend towards x plus 1 times 0. Okay, now of course you could just say that's 0, but let's actually remember we want to sort of talk about when this is going to converge. So to converge, we need absolute value x plus 1 times 0 to be less than 1. Remember, this is going to be always true. No matter what x value you plug in, once you multiply it by 0, it is guaranteed to be less than 1. So this tells us our interval of convergence. Well, we can say our radius first. This tells us, since it's always true, the radius of convergence is positive infinity, and the interval of convergence is negative infinity to infinity. So remember, where we saw an example of this in the previous video, if your limit comes out as 0, then this product is always going to be less than 1, meaning you have an always true statement, so your interval of convergence is everything. So you'll sort of notice that this limit and this radius are sort of inverses of each other. If we look back here, when we were doing this first example, we got a limit of 1/6, and our radius of convergence was 6. So the reciprocal of that 1/6 gave us the radius of 6. Here, it's a little informal, but you can sort of still think about it. We got a limit of 0. The reciprocal of 0, 1 over 0, gives us that radius of positive infinity. So there's a definitive relationship between what that limit value comes out as and that radius of convergence. Okay, let's go ahead and take a look at another one. So we want to determine the radius of convergence and interval of convergence for this power series. Sum n equals 1 to infinity, 9 to the n, x to the 2n. Now, one thing you should notice that this doesn't have just x to the n. So if we were to actually write this out, what this would look like is instead of having x, some number x plus some number x squared plus some number x cubed plus dot dot dot. Instead, this one's going to have some number x squared plus some number x to the 4th plus some number x to the 6th. So it only has the even exponents. But it's still a power series, and we still analyze it the same way. Notice that everything is just easily multiplied together and it all has powers of n, so we might as well just use root test. You could certainly use ratio test if you want, but root test will be a little bit easier. Before we get that, I'm sort of skipping ahead though, I apologize. We should always state the center. Center here, of course, is just x equals 0, because we can think about x to the 2n as really being x minus 0 to the 2n. So our center is at x equals 0. Okay, let's go ahead and now use root test. So we're going to take the limit as n goes to infinity. Absolute value, 9 to the n, x to the 2n, all to the 1 over n. All right, this absolute value, of course, is going to apply just to that x. So we can say that this is the limit. N goes to infinity, 9 to the n, absolute value x to the 2n, all to the 1 over n. All right, let's go ahead and distribute this exponent onto both faces. So we get the limit as n goes to infinity, n to the 1 over n, so n times 1 over n, that's going to be a 9, and then absolute value x, and 2n, absolute value x to the 2n to the 1 over n, and multiply those exponents, we get absolute value x squared. Once again, this time it didn't just boil down to an absolute value. All the other ones have, but this time it still has a square. Main thing, though, is that this doesn't involve an n, so we can just stick this out front. So we get absolute value x squared, limit n goes to infinity of 9. Well, that's sort of dumb. That's just absolute value x squared times 9, right? Because there's no n in this limit, so of course it's just going to be 9. Well, so to converge, we need this absolute value x squared times 9 to be less than 1. We can solve that. That's absolute value x squared is supposed to be less than 1/9. And if we square root both sides, we get absolute value x is supposed to be less than 1/3. Right? When we square root that 1/9, we get a 1/3 there. So this right here tells us our radius of convergence. So our radius of convergence is 1/3. We can go as far as 1/3 of a unit and still have convergence. It also tells us our interval of convergence, at least the sort of format of it. Since our center was 0, we can go 1/3 of a unit from there. So our interval of convergence is going to be minus 1/3 up to 1/3. And then we will need to test these endpoints individually there. Okay, let's go ahead and test those on the next page. So we now need to test the endpoints. Again, doesn't matter the order that you do them in. So let's just do the lower one first. X equals minus 1/3. So if we plug that in, we get n equals 1 to infinity, 9 to the n, minus 1/3 to the 2n. We've got to figure out some way to simplify this. Remember, we said anything that's exponential should cancel out. So let's view this as 9 to the n minus 1/3 squared to the n, because that 2n can be thought about as squaring and then raising it to the nth power. And then, of course, we equals 1 to infinity, 9 to the n. That looks like 1/9 to the n. We can multiply those together. Equals 1 to infinity of 1. Now, you might look at this and say, oh, that looks like it converges. But remember, this is a sum. So this is a sum of an infinite amount of 1s. This diverges, for sure. You could even say it diverges by test for divergence if you wanted to, because the limit as n goes to infinity of a sub n here would be 1, which is not 0. So it diverges. So unfortunately, x equals minus 1/3 is not going to be part of our interval of convergence. Let's try x equals 1/3. Should be very similar. The work is going to be almost identical. So 9 to the n, 1/3 to the 2n. So whenever you're testing endpoints, the work you do should be very similar for them. Doesn't mean they're going to have the same behavior, but the same sort of simplification should happen. So we get 9 to the n, 1/3 squared, and then all to the n. So then that's sum n equals 1 to infinity, 9 to the n, 1/9 to the n. This time, again, same thing. N equals 1 to infinity, 1 also diverges. So this tells us that our interval of convergence this time is minus 1/3 up to 1/3, but we have to put open parentheses on both those endpoints because it doesn't converge at either endpoint. It converges inside the range. Things like minus a quarter or 1/5 or 1/7 or any of those values will converge, but right at minus 1/3 and 1/3, unfortunately, it diverges at both endpoints. So if we compare this example to the first one, in the first one, we had got that it converged at both endpoints. So we saw that we had two convergent endpoints. In this one, we actually saw that it diverged at both endpoints. So notice that this is why we have to test the endpoints individually, right? In the first one, they converged. In the second one, they diverged. We will see an example in just a few moments, too, where one endpoint converges and the other diverges. So the behavior can be all different sorts of possibilities there. Okay, let's go ahead and take a look at another example then. So we want to determine the radius of convergence and interval of convergence for the sum from n equals 1 to infinity, e to the n squared, n to the 100, x plus 9 to the n. So same thing we want to do. Let's get our center. It's x equals -9. We see all these things, again, multiplied and divided, and we also notice that we have an e to the n squared. So that would be sort of a nice power to simplify. Might as well use root test again here. So let's use root test. Let's do our limit as n goes to infinity. Absolute value, e to the n squared over n to the 100, x plus 9 to the n. Absolute value, 1 over n. Notice that every time we start one of these power series sort of investigations, we always begin with ratio and root test. Also, something else you should notice as a pattern, you always start with ratio and root test, but when you check those endpoints, you never use ratio or root test. Because remember, those endpoints, if there are any endpoints, are going to be exactly where ratio and root test yield no information. So just remember, as a general pattern, we always start with ratio or root test, and then we always end, if we need to check endpoints, with other tests, never ratio and root test. Okay, let's go ahead and first take this absolute value and recognize that it applies right here. So we get that this is the limit. N goes to infinity, e to the n squared, n to the 100, and then we have absolute value x plus 9 to the n, and then all of that to the 1 over n. So let's go ahead and distribute this 1 over n exponent onto everything. We get the limit as n goes to infinity, power to a power, we're going to multiply. It looks like we're going to get e to the n. Down here, power to a power, we multiply, so we get n to the 100 over n, and we get absolute value x plus 9. At this point, we should be pretty used to taking this and popping that out front, so we get absolute value x plus 9, limit n goes to infinity, e to the n over n to the 100 divided by n. Okay, standard trick with root test, we need to rewrite this in terms of an n to the 1 over n limit. So absolute value x plus 9, limit n goes to infinity, e to the n over n to the 1 over n, and then all to the 100. Now this is nice and easy. This is going to be x plus 9 in absolute value. As n goes to infinity, this part up here is going to be approaching infinity. So I guess we should be careful. Let's give that a little arrow there. And then down here, this is going to be approaching 1 to the 100. Now, 100 is a big exponent, but this is 1 to a finite exponent, so it is just going to approach 1. So we're getting x plus 9 times infinity. So to converge, we need absolute value x plus 9 times infinity to be less than 1. There is only going to be one value of x that's going to make that true. Right? And that's when that value of x makes this not close to 0, but exactly 0. And that's our center, x equals -9. So this is only true at x equals -9. So what does that tell us? Well, it tells us the radius of convergence is 0, we can not go any units from our center and maintain convergence, and our interval of convergence is just simply the single value x equals -9. So notice that when we get a limit of infinity there, that means it's going to have a radius that is 0, and the interval is just going to be the center value. Okay, let's wrap all these up with just one last example of determining the interval and radius of convergence. So we'd like to determine the radius of convergence and interval convergence for the power series sum n equals 1 to infinity minus 1 to the n, 1 over root n x minus 2 to the n. Okay, so how are we going to approach this? Well, same thing as we've sort of been doing. We can use either ratio or root test. It might be handy to just remember that that is n to the 1/2, and then of course we can just go ahead and go and do a root test here. So let's make a note of our center. Center is x equals 2. So let's try a root test again. Limit n goes to infinity. Minus 1 to the n, 1 over n to the 1/2, and then x minus 2 to the n there. Okay, and then all of that to the 1 over n. As always, we'll take that absolute value and say that it's going to apply there, but we can say a little bit more to it. That minus 1 to the n, we know that that's an alternating piece going positive, negative, positive, negative. In absolute value, that's just going to be eliminated. So we can write this as the limit as n goes to infinity. 1 over n to the 1/2, absolute value x minus 2 to the n, and then all to the 1 over n. So we did two things there. We took this absolute value and applied it here, and we also used that absolute value to remove this. Okay, now we can go ahead and distribute this exponent. So we get limit n goes to infinity, 1 over n. 1/2 times 1 over n is going to be 1 over 2n, and then absolute value x minus 2. All right, as usual, we'll stick this guy in the front. So absolute value x minus 2, limit n goes to infinity, 1 over n to the 1 over 2n. Standard trick, got to try to figure out an n to the 1 over n sort of expression in there. So we can view this as x minus 2. Limit n goes to infinity, 1 over n to the 1 over n, and then to the 1/2. Notice that all we're really doing is just saying that power to a power, you can do the powers in whatever order. So instead of doing n to the 1/2, then to the 1 over n, we're really doing n to the 1 over n, then to the 1/2. So in this case, we know that that's going to be absolute value x minus 2 times 1 over 1 to the 1/2, which of course is just going to give us x minus 2 absolute value times 1. All right, so to converge, as always, we need absolute value x minus 2 times 1 to be less than 1, which, sort of just writing it out to stay consistent, but absolute value x minus 2 needs to be less than 1. So this right here gives us our radius of convergence. So our radius of convergence here is 1. We can go 1 unit from our center and maintain convergence. What does the interval of convergence look like? Well, we know that we're centered at 2 and we can go 1 unit. So our interval of convergence is 1 to 3. And we'll have to check these endpoints. So let's go ahead and check those on the next page. So let's go ahead and check the endpoints. We'll check, say, x equals 1 to start off with. That's going to give us the sum from n equals 1 to infinity, minus 1 to the n, 1 over root n, and then 1 minus 2 to the n. Well, that's going to give us the sum from n equals 1 to infinity, minus 1 to the n, 1 over root n, and minus 1 to the n. Now, takes a little thinking here, but this and this, well, what happens with minus 1 to the n times minus 1 to the n? You could use power rules and recognize that that's minus 1 to the 2n, but minus 1 to the 2n is an always even number. It's minus 1 to an always even exponent. And minus 1 to an even exponent is always going to be positive. So these two, when they multiply together, actually cancel out. You can also think about that as if this guy is positive, so is this one, and positive times positive is positive. And if this guy is negative, this guy is negative, and negative times negative is positive. So in other words, if you have the same alternating piece repeated, it's just going to cancel. So we end up with n equals 1 to infinity, 1 over root n. What do we know about this? This diverges as a p-series because the power is only 1/2, which is less than or equal to 1. So x equals 1 is not going to be included in our interval of convergence. Let's go ahead and check x equals 3. For x equals 3, we have n equals 1 to infinity, minus 1 to the n, 1 over root n, 3 minus 2 to the n. So that gives us n equals 1 to infinity, minus 1 to the n, 1 over root n, 1 to the n. Now, of course, 1 to the n, that's just 1, so we don't even need that. So we end up with n equals 1 to infinity, minus 1 to the n, 1 over root n. Now, what do we know about this? Well, you might say, doesn't it diverge as a p-series? Well, it does have this alternating component, though. So if you try AST, this does go to 0, and it is strictly decreasing. So this converges by AST. Now, we know that this is an example of something that is only conditionally convergent, because if you put it in absolute value, it would diverge. But remember, we're just interested in convergence or divergence here. We don't care what type of convergence for power series. So this does converge by AST. So that tells us our interval of convergence here is going to be from 1, not including 1, up to 3, but including 3. So our interval of convergence is from 1 to 3, including the value of 3. Okay, so this, along with some of the other examples, shows you that you really do need to test the endpoints. We saw an example in our first one. Let's go back and find that first one, where both endpoints converged. We saw an example with our third one, where both endpoints diverged. And now we just saw an example where one endpoint converged and one endpoint diverged. It is, of course, possible that the left-hand side could converge and the right-hand side could diverge. So you always have to test the endpoints individually. All right, so let's go ahead and wrap this up with one last example. We're not going to do any more sort of computation of the interval of convergence and radius of convergence. I think that we've done enough of these, and you guys can practice some of those on your own. But I'd like to do one more example to help us really understand the concept of the radius of convergence. So this next one is a bit more theoretical, but it really just helps you sort of strengthen your understanding of radius of convergence. So let's take a look at it. So we're going to suppose we have a power series, sum a sub n x minus 6 to the n. So notice that we're not being told what those a sub n's look like. We just know that that's the form of our power series. We're also going to suppose that the power series converges at x equals 3 and diverges at x equals 13. So we know that this x equals 3 is inside the interval of convergence, and we know x equals 13 is outside the interval of convergence. And then we have a whole host of series that we would like to look at and try to determine if these series converge, diverge, or if we don't have enough information to make that decision. So this is sort of a tricky sort of question to grapple with at the beginning, but once we figure out sort of a good way to approach it, it should be pretty easy to do. All right, so what approach should we take here? Alrighty. Having just a little trouble with the pen here. Okay, there we go. Sorry about that. All right, anyway, so how are we going to sort of approach this? So what I'd like to do is first let's identify the center of this thing. So if we look at the center here, we can immediately see that the center is at x equals 6. So we should make note that the center is at x equals 6 here. So let's draw ourselves, before we start to tackle these questions, a little diagram. Okay, that's a terrible number line. There we go. So let's put x equals 6 here. And let's label some of these other important values. We know that if we go 1, 2, 3, that would be x equals 3, and then 7, 8, 9, 10, 11. Looks like we're going to need a little bit more space there. I apologize. Let's redraw that real quick. There's 6, 5, 4, 3, so that's going to be important. 7, 8, 9. I don't need to label all those. 7, 8, 9, 10, 11, 12, and 13. Okay, so there's sort of just a quick diagram of the stuff that we have here. So we know that this is the center, and we know that right at x equals 3, this thing converges. So I'll draw that in sort of green there. And then at x equals 13, we know that it diverges. So before we start to look at these, what information does this tell us? Well, remember, if you have an interval of convergence, it has to be centered at the center. So in other words, if you have your center at 6 and you know that it converges at 3, it has to converge all the way up to 3. So in other words, any of this stuff in between, it also has to converge at, because you can't have it where it converges for a while, then diverges, and then goes back to convergent. We said there were only 3 possibilities. Converges everywhere, which we know is not going to happen because it diverges at x equals 13. Converges only at the center, which we know isn't happening because it converges at x equals 3. Or it converges at some interval centered at the center. So it has to converge all along here. But remember, it has to converge on an interval centered at the center. So if it converges this way, it also has to converge the other way. So it has to converge out to here, which of course would be equidistant at 9. So if it converges out to 3, it has to converge up until 9. All right, what do we know about it diverging? Well, if it diverges here, then it has to also diverge further out. Because if you are further than this, it can't suddenly converge, because then we'd have convergence, then some divergence, and then some more convergence. That wouldn't be an interval centered at the center. So we know that once it starts to diverge, it diverges the rest of the way out. But that means it also needs to diverge on the other side, because you can't have an interval that converges more on one side than it does on the other. So if we figure that distance, that's 6 to 13, which is 7 units, I guess. So we got to go 2, 1, 0, minus 1, I guess, would be equidistant. And that means it diverges all down here. So just by the limited information we know that it must converge in here, and it must diverge out here. Now, what about in these sections? Well, unfortunately, these are going to be areas where we don't know what's going on. We don't have enough information because they're further than something that converges, but they're closer than something that diverges. So unfortunately, these are going to be sort of no man's land. We don't actually have enough information there. Okay, so let's take a look at this. We might be tempted to say, okay, this is x equals 2, and I guess 2 would be like right there, so no information or not enough information. Well, we got to be careful, though. Remember, ours is x minus 6. So what x value are we plugging in to get a 2 there? Well, clearly, that would actually be when x equals 8. If we plug in x equals 8, 8 minus 6 gives us that 2. Well, x equals 8, if we look at that, that would be 7, 8. It would be right there. That's solidly in the convergent area, so we know that this guy is going to converge. So this series must converge based on the information we were given. What about this? Well, negative 9 to the n. What x value must we be plugging in? X minus 6 needs to be negative 9. That makes x equal to negative 3. Negative 3, well, that would be negative 2, negative 3 down here. Solidly in the diverge range, that must diverge. Okay. What about this here with a 5? Well, that means that the x must be like 11. So this would be x equals 11. Wrong color there, sorry. That would be x equals 11. So x equals 11, there's 9, 10, 11. Notice that's right in the area where we don't know. It's further than something that converges and closer than something that diverges. So unfortunately, this one, all we would be able to say is not enough information. We can't tell based on the information we've been given. Okay, what about this here? Well, if we get a 3 in there, since it's x minus 6, that must mean that x was 9. So this would be x equals 9. If we go to our diagram, x equals 9 is right there. Well, we might be tempted to say, well, that is in the convergent range, but notice it's actually equidistant, right, to what we know converges. So theoretically, this might be our interval of convergence. And as we know, if it converges at one endpoint, it might actually diverge at the other endpoint. But we don't know. So unfortunately, 9 is also an example of not enough information. It's equidistant from something that converges. That could be convergent or it could be divergent. What about this last one then? Well, -7, what would we plug in to get -7? That would be x equals -1. If we go to our diagram, x equals -1 would be right there. That would be equidistant from something that diverges. So unfortunately, once again, that's going to be not enough information because it might diverge there or it might converge there. So these last three are all examples where we don't have enough information. So what's the point of this one here? Or why did we spend some time talking about it? Just to again strengthen your guys' understanding of what it means to have an interval of convergence. An interval of convergence is not just some interval, it's an interval that's centered at the center, meaning that if we know it converges somewhere, then it must converge all the way out to that value in both directions. And as soon as it diverges, we know it continues to diverge further out. So very, very important to recognize that the interval of convergence isn't just any random interval. It has to be an interval centered at that center. All right, this wraps up our section 11.8, which is our introduction to power series. In our next video, we'll be moving into 11.9, where we'll investigate why we want to understand power series. And we'll see that that directly relates to representing functions as power series.